Okay, right. In the previous class, we have seen the kinetic molecular theory of gases, and we have seen the postulates and also the justification of the proposed postulates. And this is what we have seen in the last class, that is the kinetic molecular theory is applicable only to ideal gases. And the first postulate, the gases are large number of minute particles. When you measure the actual volume of the gas particles and the total volume of the space, the volume of the gas particles is negligible. And also in the second postulate, we have seen the gaseous molecules are in constant rapid motion. And in the third postulate, we have seen while the gas molecules move here and there, they experience a collision. That is a collision among themselves, and also they collide on the walls of the container, and the collisions are completely elastic, which means that while colliding they do not lose energy. And also the gas molecules do not show attractive force, therefore the motion is a totally independent motion. It is not influenced by the attraction or repulsion of the gas molecules. And also the pressure experienced inside a container is due to the bombardment of the gas molecules on the walls of the container. So when you wanted to justify these postulates, the first justification that was given is that at a normal temperature and pressure, when you measure the total volume of oxygen, hydrogen and nitrogen, or any other gas, it comes around only 0.014% of the total volume of the container. Therefore, it is the first postulate is confirmed that the gas molecules are very minute particles with negligible volume. And the next thing, when you see the smoke, when you pass the light through the smoke, you can see the Tyndall effect. That is the path of the light being seen, which is scattered by the carbon material. And this carbon material which is present in the air is continuously bombarded by the gas molecules, the rapid motion of the gas molecules, and hence you can see the zigzag motion of the carbon. So which proves the other postulates that the gas molecules are in a constant motion. And the third one, if the gas molecules lose energy, then on continuous motion and the continuous collision, the gas molecules will continue to lose energy, and finally they will have zero energy and they will come to rest, which is not happening at all. Even if you take a container and fill it with gaseous molecules and keep it aside for 500, 600 years and come back and see, even then you can see the motion of the molecules. So which shows that the motion of the molecule is a completely independent of the attractive force, and also the collision is elastic, and hence I can say that the gas molecules do not lose energy while colliding with each other or colliding on the walls of the container. And also when you leave the gas free, it shows expansion, which shows that the molecules are moving away. So this proves that the molecules do not have attractive force among themselves. And also in the closed vessel, the pressure is due to the bombardment of the gaseous molecules on the walls of the container. So these are all the theory, the kinetic molecular theory and their justification. And today we are going to discuss a little more deeper concepts, which are much important and which needs much of your attention to understand. Let us discuss the pressure of an ideal gas. So from the postulates, the gas molecules are assumed to be point masses, and they are in a random motion, and they collide with each other. And these statements about the gaseous molecules permit us to follow the laws of classical mechanics for the motion of gaseous molecules. So when I was teaching the quantum mechanics, I have clearly explained to you the difference between the classical mechanics and the quantum mechanics. So the classical mechanical laws can be applied for the motion of gases in a container. So look at the picture. This is a cubical container. Why it is taken as a cubical container? Just to make us convenient to do the calculations. If the dimensions are different, because the pressure is not going to change with the shape of the container. It is independent of the shape of the container, but for our convenience, we are taking the cubical box. So in this cube, a number of gaseous molecules are there. If one molecule moves in this direction, other molecule moves in the other direction, and another molecule moves in another direction. So like this, they are all moving in various directions. Let me say N is the number of molecules, and V is the volume of the container. L is the dimension. Dimension means this is a cubical box, therefore I can say the length or breadth or height all are equal. The L is the dimension, and M is the mass of the gas. Now look here. Suppose a molecule is moving in this direction with the velocity v and with the mass m, and hence the momentum being m into v, and it goes and it collides on the wall of the container, and then it takes the other direction and it comes back. I have already told you that while colliding on the walls of the container or on colliding with each other, the gas molecules are not losing their energy, means that is the linear momentum is conserved, which is not changing. Therefore, it comes back with the same linear momentum, but opposite in direction. So this is the transfer of linear momentum. Now look here, the walls are perpendicular to x, y, z axis of a Cartesian coordinate system. So look here, suppose this is the x axis, this is the y axis, and this is the z axis, means look at the walls. Suppose if you take this wall, this is perpendicular to the x axis, and this wall is also perpendicular to the x axis. If you take the front and the back walls, they are perpendicular to the y axis, and if you take the up and the bottom walls, they are perpendicular to the z axis. That is what is mentioned here. All the 6 walls. A cubical box contains 6 faces, and these 6 faces are considered the 6 walls, and these 6 walls are perpendicular to x, y, and z axis of a Cartesian coordinate system. So 2 faces are perpendicular to one axis. Why I am telling you this? If you consider the velocity of the gaseous molecules is c, that c may be in any direction, but this motion in any direction can be resolved into 3 different motions in 3 different axes. Look here, the c, the velocity, can be taken as u in the x-axis, it can be taken as v in the y-axis, and it can be taken as w along the z-axis. But what is the relation between u, v, w, and c? The relation is this: c square is equal to u square plus v square plus w square. Now look here, the change in momentum on the wall. I am going to observe what is the change in the momentum. And we have already discussed here, there is no quantitative change in the momentum. There is only change in the sign, which means only there is a change in the direction. So what I can say, suppose a molecule is moving towards the wall in a particular momentum and it comes back from the wall with a different momentum, means the change in momentum can be measured as the previous, the final momentum minus the previous momentum. So look here, the previous momentum mu, final momentum minus mu. Therefore, they are getting added. It is 2 mu. That is the change in momentum. There is only one change, which is the change in the direction. Therefore, the change in the momentum becomes 2 mu. Now, look at here. This is another important idea. You should make use of your imagination to see the things happening in your mind. See, this is a wall. This is a wall. A molecule is here. And this molecule goes and hits on the other wall. And there it just changes its direction. And then it comes back. It comes back to this one. Look here, the total length is L. The distance between the two walls is L. If the gas molecule is traveling with a velocity u, then the time taken to travel all the distance is L by u. Suppose if you want to calculate the time taken by the gas molecules to come back to the same place, that will be 2L by u. So 2L by u is the time. So that is the time taken for a gas molecule to come back to the original place. Now look here. So change of momentum with the change in time. That is the rate of change of momentum I am going to calculate. This rate of change of momentum is nothing but force. Force is rate of change of momentum. I have already discussed this dimensional analysis in the quantum mechanics, and which says that the rate of change of momentum is a force. So delta px is the rate of change of, delta px is the change in momentum divided by delta t, the change in time. We have already calculated what is change in momentum. It is 2mu divided by the time is u by L. Therefore, you are getting 2mu square by L. Similarly, you can find out the change of momentum in all the three directions, which can be written as 2m by L u square plus v square plus w square. So this u square plus v square plus w square is nothing but a c square. So it is 2mc square by L. Similarly, if you can calculate for all the molecules inside the container, which is equal to summation of everything for I is equal to 1 to n, it is sigma I is equal to 1 to n 2mci square by L. So which is the 2m and the L, they are not going to change with the summation, therefore they can be taken out, and your summation I is equal to 1 to n ci square. This ci square is called mean square velocity. It is called mean square velocity. So that c square is equal to sigma ci square divided by n. N is the total number of gaseous molecules. Therefore, the summation of ci square can be written as n times the mean square velocity. Therefore, this can be substituted in this equation, and you are getting the total change in momentum by the time is equal to 2m mean square velocity divided by L. Now, according to Newton's second law, The dP by dt is the force. So you should understand what is force. Force is rate of a change of momentum. See, when I was teaching the quantum mechanics class, I have discussed this with the dimensional analysis, how the rate of change of momentum becomes the force. Force is equal to mass times acceleration. Acceleration is the rate of change of velocity. Therefore, the m into velocity is momentum. So the rate of change of momentum will give you mass times acceleration, which is force. In the case of a gaseous state, in the case of a gaseous state, force per unit area is momentum. So look here, force by area is momentum. That is, the force acting per unit area is momentum. So the force we have seen in the previous thing, that is 2m n mean square velocity divided by L. Area you should understand. So see, what is this area? Area is the total area of all the 6 faces. We have taken a cubical box. Hence the area of one face is L square. So this L square area multiplied by 6 will give you the total area. So pressure is acting on the entire area. So the pressure can be written as pressure is equal to 2mn mean square velocity divided by, already one L is there. Now I am going to divide this by area 6L square, and this 6L square and this L will become 6L cube, and this 2 and this 6 can be cancelled, and finally you are getting mn mean square velocities divided by 3 times volume, because L cube is volume. So in this L cube is volume. In the root mean square velocity is nothing but the square root of mean square velocity. And that is, we have already seen, that is sigma ci square divided by n square root. Let me say this is equal to c, the root mean square velocity. Hence I can write the mean square velocity is nothing but root mean square velocity square. Therefore, pressure can be written as 1 by 3v m n c square. If you take this volume to the other side, you will be getting PV is equal to 1 by 3 m n c square. This is called kinetic gas equation. And also this equation is applicable only for ideal gases. This equation is not applicable for real gases for one particular reason, and we have assumed that the ideal gases do not show any intermolecular forces such as attraction or repulsion, but real gases, they show the intermolecular forces. If the intermolecular forces are present, then their motions are influenced by the intermolecular forces. Therefore, this equation cannot be applied for real gases, but this equation is very well applied for ideal gases. So this is called the kinetic gas equation. Now look here. Now we are going to discuss a few important terms in the case of a collision theory. Collision diameter. This is the first point to be understood when you discuss the collision theory. The gas molecules, they move in a random motion, and during their motion they hit on each other. This hitting is called collision, because the gas molecules are taken as a point masses. So what will happen when these point masses come closer? At a particular point, they are sufficiently closer, and there happens the inter-electronic repulsion, because every gas molecule is moving with its own electron cloud and also the nucleus, and the other gas molecule is also moving with its electron cloud and the nucleus. And when they are coming closer, there is a lot of possibility for them to feel the like charges present in the other atom, and they will experience a mutual repulsion, and because of that repulsion there will be a reversal of the direction of their motion. So they are moving forward and they are approaching each other at a critical distance. They feel the mutual repulsion, and the reversal of the direction of their motion takes place and they go away. At that minimum distance, or that maximum close proximity, the maximum closeness at which the reversal takes place, or the distance between the centers of the two molecules at the point of their closest approach, that distance is called the collision diameter sigma. See, if you consider a gas as a rigid, hard sphere of radius sigma, then the volume, that is the effective volume of the gas atom, is a 4 by 3 pi sigma cube. So collision is an event in which the centers of the two identical molecules come within a distance of sigma from each other. So that is the minimum distance, or that is the closest distance possible before they revert their direction of motion. So before that, before attaining the sigma, they will move close to each other. After coming to that closest approach, they will start repelling each other, and the reversal in the direction of their motion takes place. So this is called a collision diameter. So the gas molecules are moving in all directions, and the gas molecules are approaching each other, and the collision is a completely elastic. There is no energy loss during the collision, and when they come closer, what is the closest approach that is possible? Because when they are very close to each other, they feel the mutual repulsion, and hence the reversal of the motion will take place. And before the reversal of the direction of their motion, what is their closest approach? That closest approach is known as the collision diameter sigma. So next, collision cross section. See, the gas molecules are moving here and there, and they not only simply move, they do the transport things also, and they show the transport properties also. And these transport properties are viscosity, diffusion, and thermal conductivity. See, for example, suppose if you want to cool down a hot coffee, you are having a coffee and the coffee is very hot and you want to cool it down, so you switch on the fan. Actually, what is happening is the gas molecules or the air molecules coming from the fan, they hit the coffee and they take the thermal energy, and the thermal energy is taken off by the gas molecules. That is why the coffee is getting cooled down when you are keeping the coffee in a breeze or in a fan air. So these are all the transport properties. What is viscosity? Viscosity is a resistance to flow. What is the resistance is shown by a fluid to flow. What is inertia? It is the resistance shown by an object to move. So viscosity is a resistance to flow. What is diffusion? It is the escaping, or no, the diffusion means, suppose if you take a beaker full of water and put a drop of ink, you can see the ink molecules getting diffused and the entire water becoming homogeneous in color. So this is called the diffusion. Suppose if you are living in a closed room, air tightly closed, and you are inside the room, and you can feel that the oxygen ppm, oxygen level comes down, In such a situation, if a small window is open, what will happen? You can see the diffusion of the fresh air through diffusion means it is not effusion. You should understand the difference between diffusion and effusion. Effusion is escaping of the gas molecules through a small hole. Suppose if there is a hole in your bike tire or a cycle tire, you can see the air coming out. That is effusion. Diffusion means a particular component getting filled in a already existing environment. That is when you are in a closed room, if the oxygen ppm is coming down, when a small hole is open, it doesn't mean that the entire air is coming out. The oxygen will diffuse into your room. That is called a diffusion. So you should understand the diffusion and the effusion. So the transport properties like viscosity, diffusion, and the thermal conductivity, these are all because of the continuous and the uniform motion or the random motion of the gaseous molecules. Now I want to discuss this one particular point, what is collision cross section. The collision cross section is the cross sectional area of an imaginary sphere surrounding the molecule into which the center of another molecule cannot penetrate. Look here, two molecules are hitting each other. These spheres, something like the billiards, golikundu, these spheres, how hard they can hit each other. If you cut the sphere into two halves, you can see a circle with the radius sigma. What is sigma? Sigma, what is sigma? We have already seen it is collision diameter with the sigma, and that area, that is pi r square. Now area of the circle, you see this is the sphere. If you take the cross sectional area, this is a circle, and the circle, the area is a pi r square. Here the radius is sigma, which is collision diameter. So this is pi sigma square. So effective area of the target is pi sigma here. So not the surface area of the sphere. You should not get confused with the surface area of the sphere. This is only the area of the cross section of the sphere. So what is collision cross section? It is the cross sectional area of an imaginary sphere surrounding the molecule into which the center of another molecule cannot penetrate. Another molecule cannot penetrate this area. It can hit here, but it cannot penetrate this area. This is called collision cross section. So the next idea, I will discontinue the meeting and please join again.